All right. We're going to talk now about the gambler's ruin problem. So the gambler's ruin problem is really one of those classic probability problems. And we now have all of the ingredients necessary to deal with the gambler's ruin. Okay, so the gambler's ruin problem, think about it this way, is we're going to think about it in terms of having a coin toss. Okay, so we have two players again. So we're going to again have two players, and we're going to just refer to them as A and B. Player A, player B. We're going to bet. They bet on successive tosses of a coin. What I mean by that is they're just going to keep tossing tosses of a P coin. So probability of heads is P. Um, so they just keep tossing it. Okay. And then on each toss, A wins. No, if it's heads, then A wins $1 or 1 unit from B. And if it's tails, B wins 1 unit from A. And they're going to continue until one of the two players is ruined, meaning one of the two players is out of money and the other one has all the money. So we continue playing until A or B is ruined, has no money, can't play anymore. So has zero. Okay. So the question is, for our sake, question is suppose, so we're going to suppose that player A starts with capital or starts with I dollars and B starts with capital N minus I dollars. The question is, what is the probability that player A wins the game? So think of it this way. We're player A and the casino is player B. We're going to go into the casino and we're going to try to beat the casino out of all of its money. What's the chance that we can do that before we go broke ourselves? Okay. How are we going to set this up? So this setup is pretty interesting. And we have to use a number of the tools in our toolbox. Number one, so let's think of it this way. So we're going to think of it this way. There are N total dollars to be had. We start with I, or player A starts with I, and the opponent starts with N minus I. So add those up, you get capital A. Okay. The way we're going to do this is we're going to apply to our main techniques. Condition on the first step. Appeal to independence. of tosses. So we use that to, we condition on the first step. We apply the law of total probability. So those two go together. When we do that, we can then leverage independence to get a nice expression that sets us up a recursion. And we can solve that recursion by solving a collection of difference equations. So there's actually quite a few components to this. So it's not a simple problem. And being able to solve this, it's a nice it gives us a nice tool in our toolbox. Okay, so what are we going to do here? Well, we're starting at, so we're going to try to condition on the first step. Okay, and we're going to imagine that, well, after the first step, if heads happens, we're going to end up, player A ends up with I plus $1, and if tail happens, ends up with I minus $1. And so we have to realize that the probability of winning having I dollars is different than the probability of winning if we have I minus $1 or I plus $1. So let's define some notation where we're going to write pi sub I to be the probability that player A wins, given that player A starts with, player A starts with I dollars. And the total dollars is assumed to be N, capital N. And this is for all values of I from 0 up to capital N. And so we have to condition on that information because after the first toss, player A is not going to have I dollars anymore. Player A is going to either have I plus $1 or I minus $1. And then we appeal to independence then to say, well, we then have either I plus $1 or I minus $1, but it's like the game starting all over again with a different initial state. And we're going to use that to set up the recursion, and that recursion is going to lead us to a nice way to solve using difference equations. So from this definition, we have some initial conditions that we know the answer to right away. The first is that if we start with $0, we can't win. It's impossible. Game's over. So we know the game is over before it starts if we either start with $0 or we start with all N dollars. Start with all N dollars, we win. Probability of 1. Now for all other I, we're going to condition on the first step. Okay, so we condition on the first step. What do we have? Well, pi I is what? Well, the probability we win, given that we start with I dollars, is equal to the probability, there are two possibilities, right? Well, let's condition on the first step. Well, the first possibility is that we flip ahead. So probability that the first toss is ahead times the probability that A wins given start at I, first toss is ahead, plus probability that the first toss is tail, probability A wins the game given A starts at I and the first toss is tail. Well, the probability of a head is P. Probability that A wins, given we start at I and then the first toss is ahead, is the probability that A wins, given that we start at I and then we have I plus 1 before the second toss. And I'm writing this out pretty explicitly to make sure that I emphasize. Now Q, the probability of a tail is Q, 1 minus P. Probability that A wins, given that we started at I. And then if the first is a tail, we're going to have I minus 1 after the first toss and before the second toss. We have to then interpret these conditions here a little bit carefully. And what we can realize is that the condition, the probability that A wins, once we know what the current dollar value is, the past dollar values don't matter anymore. Right, so this could be the 100th toss. If A has 100 as I plus $1 after the 100th toss, the fact that A started with I dollars or some other value is irrelevant, and the way that we got here is irrelevant. We have this much money left, and everything that comes after it is independent. So this is just like the game is starting over at each step. And this is like saying that the game starts over and I has I minus $1 or A has I plus $1. Well, we define those by the pi i's, right? So this gives us now an expression which is P times pi I plus 1 plus Q times pi I minus 1. And just to be clear, we're defining Q as 1 minus P. All right. So now what we need to do is what we're going to end up with is solving for we have a system of equations here. And it's not immediately straightforward, but what we need to do is we need to solve a recursion of this form. So we have a value x sub n, we have a sequence of x's, and there's a constant c1 times x n minus 1 plus c2 times x n minus 2. And this is what we have. In the case of Gambler's Ruin, how does this look? Well, we have to realize that the largest index is here, and then they're decreasing here. So in the case of Gambler's Ruin, what we have is pi n equals P. No, sorry, pi I equals P, pi I plus 1 plus Q pi I minus 1. And let's rewrite it to bring the pi I plus 1 over here because that's the highest value. So this is P equals pi I minus Q pi I minus 1. And we rearrange to get pi I plus 1 equals 1 over P pi I minus Q over P pi I minus 1. So this is a second order, this is called a second order recursion. This is a second order recursion, meaning we have a recursive relationship between a sequence of variables, x1, x2, x3, x4, etc., why that's recursive is that we say that we define xn as some function, as some fixed function of of other elements of the sequence. In this case, the two prior elements of the sequence. So that's what makes it second order. And what makes it a recursion is that these constants, this relation, the nature of this relationships is the same as we move along the sequence. Right. So if you've ever heard of like the Fibonacci numbers or any sequences like that, those are examples of recursive definitions of a sequence. So we have a recursive definition of a sequence as a recursive relationship, and now we need to be able to solve this. Okay, so this is a second order recursion. In the formula above, C1 is 1 over P, C2 is minus Q over P. Okay. Okay, now we've set up the recursion, and now what we want to talk about is solving the recursion, and in particular solving what's called a difference equation. So thing to focus on here is that this is our main recursion. And what I want to set up is what's called a difference equation, is that I can get a very simple expression in terms of the differences in the probabilities from I to I plus 1. And the way that we could do that is by realizing, first of all, that P plus Q is equal to 1. So something we can do is we can actually think about splitting pi I up as P times pi I plus Q times pi I. Okay. And the reason why we do that is what it allows us to do is allows us to rearrange the P's on one side and the Q's on another side. So I'm going to keep the P's, I'm going to put the P's on the left side, but I'm going to put it in reverse order. So I'm going to put P times I plus 1 minus P times pi I. And then I'm going to have Q times pi I minus Q times pi I minus 1. So I'm just rearranging both sides. And then what I'm going to do is I'm going to define delta I. It's going to be defined as pi I minus 1. So when I factor out the P here, I get pi I plus 1 minus pi I. That's delta I plus 1 is equal to Q times pi I minus 1, which is delta I. And I have this for all I from 1 up to n minus 1. Okay. And by my boundary conditions, remember what the boundary conditions were. These boundary conditions here, what do they imply? Well, let me just finish this off here. This is Q over P times delta I. Okay. So these boundary conditions and the boundary conditions imply, whoa, what the, and the boundary conditions are pi 0 is 0, pi 1 is 1. What they tell us is delta n. Well, really all they tell us is that delta 1 is equal to pi 1, which is significant. What it also tells us though is that if we add up all the deltas from I equals 1 to n, we add them all up. This is a telescoping sum. right? So in other words, I have so what I'm going to have here is I have pi n minus pi n minus 1. And then I'm going to add pi n minus 1 minus pi n minus 2 and so on. Pi 2 minus pi 1. I know, I'm sorry, pi 1 minus pi 0, which is just 0. So what happens in a telescoping sum is you're left with just the first and the last. Pi n minus pi 0, which is just 1 minus 0 is 1. So that turns out to be very important for us, as we'll see. Okay. So first thing is that we want to use this. And the way that we use this is we say, okay, for each I from 1 up to n, what we can say is we can say that delta I is equal to Q over P times delta I minus 1. But delta I minus 1 in and of itself has this same relationship. This is the beauty of the recursion. So delta I minus 1 is equal to Q over P times delta I minus 2. And so on and so forth. Delta I minus 2 is Q over P times delta I minus 3. All the way until we end up with Q over P to the power I minus 1 times delta 1. But remember, delta 1 is pi 1. This is delta 1. We can just replace pi 1 because pi 1 minus pi 0 is pi 1. Pi 0 is 0. Okay, so that is an expression for all of the i's. And then that's one thing. And then the other thing is that we have this piece here, which is that if we add up all the delta i's, what are we left with? We add up all the delta i's, what are we left with? We're left with 1. On the one hand, we're left with 1. But on the other hand, we actually have an expression for each delta I, which is Q over P to the I minus 1. That's pi 1. Pi 1 is the probability of winning the game given that A starts with $1. Well, this is a partial geometric series. So we can factor out the pi 1. I can do a re-index from 0 to n minus 1 of Q over P to the I. And this is a partial geometric series, which has a closed form expression. Closed form expression is 1 minus Q over P to the power capital N divided by 1 minus Q over P. This is provided that Q is not equal to P. So provided P is bigger than Q. Okay. P is less than Q, we can still do the analysis, but we just have to be a little careful. If P equals Q, we're gonna deal with that in a bit. Okay. So what does this tell us now? Is this tells us that pi 1 is equal to, we just flip it around. We have we have the 1 is pulled down here. We get the reciprocal 1 minus Q over P divided by 1 minus Q over P to the power N. Okay. And then in general, what can we do next? Well, in general, we know that we have an expression now. We know that delta I equals Q over P to the I minus 1 times pi 1. Right? So in general, delta I is Q over P to the I minus 1 times pi 1. So it's Q over P to the I minus 1 minus Q over P to the I to the I. Denominator doesn't change. What we end up seeing if we work through this is, well, we also know that delta I is equal to pi I minus pi I minus 1. And so a little bit of work here will give us what we need. The work is going to be that in general, pi I is 1 minus Q over P to the power I divided by 1 minus Q over P to the power N. So this is in the case where P does not equal to Q. Now, in the case where P does equal to Q, then this corresponds to the playing of a fair game. Okay, everything's the same until here. Everything's the same until here. Okay. So we still end up with an expression. We have the same difference equation. We have everything like that. We still have pi 1 equals, oh, we have 1 is equal to pi 1 sum I equals 1 to n of Q over P to the power I. But now Q over P is 1 because Q and P are equal. So this is just adding up 1 n minus 1 times, or n times, I'm sorry. So it's pi 1 times n, and we get that pi 1 equals 1 over n. And then what we have in this instance is same expression here as well, that delta I plus 1 is equal to Q over P times delta I, but Q over P is, of course, 1. So the differences are just the same. So what does that tell us? Well, that tells us that in general, pi 2 minus pi 1 is equal to pi 1 minus pi 0, but pi 1 minus pi 0 is just pi 1. Pi 1 is just 1 over n. So what we have is pi 2 minus 1 over n equals 1 over n. We get pi 2 equals 2 over n. In general, what we would get is, if we started with delta I over here, delta I minus 1 over here, and then we consider adding up to get a telescoping sum, right? So we get delta I minus 1, etc. And we build up the recursion that way. What we observe is that pi I in general is equal to I times pi 1. Of course, pi 1 is 1 over n, so it's I over n. So in this case, pi I equals I over n. All right, so what is this telling us? This is in the case where P is equal to Q. And so it's a fair game. Okay. So it's an interesting, well, first of all, very interesting problem from a mathematical problem, and interesting to get these closed form solutions. What's especially interesting, as far as I'm concerned, is to think about the possibility of playing a favorable game or playing a fair game. So the first thing is, if we play a fair game, and this is the case where P equals Q, why that's fair is it's not because the probabilities are necessarily equal, it's because in some sense the expected values are equal, but we'll get to that concept later. It's a fair game means that there's a chance to win. But of course, the chance of winning depends on bankroll, right? So, the chance of winning depends only on bankroll at that point. What we mean by that is person with more money has a better chance of winning. Pretty obvious intuitively, but I mean, maybe it's not so obvious. It's not guaranteed, so to speak. But what it's saying is that if we're playing a fair game, the person with the higher bankroll has the higher chance of winning, to the point where if n is much, much, much bigger than I, so in other words, if player B is much richer than player A, then the probability that A wins, given starting at I, which is I over n, is really, really small. It's negligible if the bankrolls are so out of whack. So this is why, this is why in general, even if we're playing a fair game, of course, the person or the company or the business with more resources has a better chance of winning the game. Not because they're necessarily better, but because the randomness is on their side. right? They can afford to take the randomness, to take the volatility in their bankroll, and eventually the volatility is going to ruin the poorer of the players much more often than not. Okay, so that is kind of a mathematical justification of a pretty obvious or intuitive observation, is that even if things are fair in a sense, the party with the higher bankroll has a better chance of winning. This is why in a poker tournament, what you'll see is at the very end of a poker tournament, sometimes, if it gets to a heads up situation, and one player has a much bigger bankroll, a much bigger stack of chips than the other. And the way the tournaments work is that they plays until one player has all the chips. So if one player has that much more chips than the other, the strategy, I mean, this is not a perfect description of an optimal strategy, but the strategy becomes more and more that the player with the smaller bankroll more or less should just go all in every hand, or should go all in almost every hand, because there's really no skill left at that point. The cards are being distributed at random, and there's no time left for the player to really wait and play out and pick a good hand. And every hand that player folds or loses, even if they lose just a small, just lose the antes or the blinds, they reduce their chips even more, and they have even less of an opportunity to win. So they're just trying to kind of get their heads back above water, in other words. So that's interesting. Now, here's another interesting thing. Let's look in the case where P is not equal to Q. So let's suppose if P is bigger than Q, so player A has the advantage in this case. Player A has the higher chance of winning each roll. I shouldn't say that player A has an advantage, because player A is going to be assumed to have much less money than player B. But in this case, the probability that player A wins. So let's suppose again that N is much, much, much bigger than I. That's all I mean by these three greater than signs. It's not really a formal, it's just saying it's very, very much bigger. Then pi I, in this case, we've already calculated 1 minus Q over P to the I over 1 minus Q over P to the N, which for very large value of N, so if N is very large, effectively infinite, this is pretty much 1 minus Q over P to the I. And what's interesting about this is bigger, this is positive. This is positive for all I. So what's interesting about that is that even if player A starts with a very, very a minuscule a minuscule bankroll compared to player B, even if player A starts with only $1, if player A has an advantage on each toss, if the odds are in player A's favor, there's a non-zero chance that player A can win this game and actually ruin the casino. And so the flip side of the first example, where the game was fair, but the person with the bigger bankroll just has such a built-in advantage that they really can't lose in that case. That's not true when the odds are in the favor of the opponent, even if there's a big bankroll discrepancy. And so to bring this into a different scenario, if there's a skill advantage that one player has over another, and I'm equating the skill advantage to be this P being bigger than Q, then a player with a skill advantage, even with a huge resource disadvantage, can still overcome that disadvantage with some positive probability. So that's another interesting consequence of the gambler's ruin problem. All right, so gambler's ruin, very important problem. A lot of implications, just a lot of interesting things coming from it, and that's going to be the end of this section. And the next topic is to formalize things a bit more in the context of well, in terms of what's called random variables. And so we'll do that next time.